Hello everyone. So previously we had discussed on the red black tree algorithm, right? So today we'll be discussing on the topic AVL tree algorithm. Yeah. So let's see what the definition part say here. Let's see what the let's see what the definition states here, right? An AVL tree is a self-balanced binary search tree, right? Similar to the tree factory. An AVL tree is a self-balanced binary search tree where the height difference, nothing but the balance factor between the left and right subtrees, height difference between the left and subtrees of every node is at most one. Right? So very simple to understand. Height difference between the left and the right subtrees of every node is at most one, right? At most. So this word is very important. At most one. So this ensures that search, insert, and delete operations always take big of logarithmic end time, right? So this ensures that search, insert, and delete operations always take big of log n this one time. Right. So now let's go with the explanation part. So in a binary search tree, nothing but the BST, inserting nodes in the sorted order makes the tree skewed and degrades performance to big of n. In a binary search tree, inserting nodes in the sorted order makes the tree skewed, right? So inserting nodes in the sorted order one by one, right? Ascending order makes the tree skewed and degrades the performance to big of n. Binary search tree, BST, we know this one, right? An AVL tree, what it does, it fixes this by rotating the nodes whenever the balance factor becomes less than -1. Yeah. AVL tree, what it does, it fixes this by rotating nodes whenever the balance factor becomes less than -1 or greater than +1, right? It shouldn't go less than -1 or greater than +1, right? After insertion or deletion, right? So this is fine. There are four types of rotations used to restore the balance. So these are the four types of rotations. I'll just read this one out loud. Listen to this carefully. Right rotation, nothing but double L. Yeah. Uh, Left rotation, nothing but double R. Left right rotation LR, and the right left rotation nothing but RL, right? So each rotation ensures that the height of the tree remains balanced, not less than -1 and not greater than +1, right? Preserving the logarithmic time complexity for operations. Preserving the logarithmic time complexity for the operations. I hope this is fine, man. Let's do one thing. Let's move on with the let's move on with the coding part actually. Yep. So let's move on with the coding part. So first thing, let's go with the node class that represents each node of the AVL tree, right? So I'll just give here class node. Yeah. So within the node class, I'll just go with actually init. So this is fine. Along with the self, I'll just go with the key as well. Yep. So this is fine within the initialization part. First, let's go with the node's value, right? So I'll just go with self dot key equals. Let me initialize this one to the right. Also, let's go with a pointer to the left child as well as the right child. First left. So let me set this one to none, and also right. Let me set this one to none as well. Yep. So these two things are fine. Finally, initial height of the node is always 1. Let's set the height to 1 as well. Right. I'll just go with the height here. Let me initialize this one with a value 1. Yep. Next, let's do one thing. So let's go with the AVL tree class that supports insertion and balancing, right? So I'll do one thing. Yep. Let me go with a class AVL tree, right? So I'll just go with AVL tree class here. Yep. So this is fine, I believe. First thing, let's do one thing. Let's go with a function to get the height of the node. Yeah. I'll just go with def here, get height get height. So along with the self, let me pass the root as well. Yep. So within the get height function or the helper method, if not root, then I'll just return 0. I'll just return 0. And also let's return, I'll just return here this one root dot height. Yeah, root dot height. So this is fine. Yep. So the next step, let's go with a helper method get balance, right? So let's go with a helper method get balance, nothing but function to get the balance factor of a node, right? So I'll just go with def balance. So this is fine. Along with the self, I need the parameter root here. right? So this is fine. Within the get balance method, if not root, then we have to return 0 in that case. Yep. So this is fine. The next part is else. Let's return. I'll just go with get height. Yep. So this one, I'll just make this one capital H. Yep. So this is fine. 1 second. Yeah. Let me go with get height here. Let's call the method get height here. So I'll just go with root dot left. It has to show, not showing. Let me type this one. Root dot left minus root dot right actually. This one has to be O. Not 0 man. O root dot right. Sorry. What am I doing man here? 1 second. Just go with a get height of root dot right. Yep. So this is fine, I believe. Yep. So we are done with the get height and the get balance helper method, right? So now we have to go with these rotations. One is LL rotation, nothing but right rotation. Another one is RR rotation, nothing but left rotation. And yeah, these things we have to do. Right and left rotation we have to go with, and then we can just go with the insert as well as the this one insert as well as the deletion, right? So let's do one thing. Mm, yep, let's go with the right rotation actually. Let me go with here right rotate of, let me go with self comma y. So this is fine. So within the right rotate method, so let's set x as y's left child, right? So I'll just go with x equals y dot left. This is fine. And t2 equals x dot right. Yep. So this is also fine. The next one is x dot right. Let me assign this one to the y. So this is fine. And also y dot left. Let me assign this one to the t2. Sorry. Yep. So this is fine now. Assign this one to the t2. Now we have to update the heights of the rotation, right? So let me copy paste this one. Just give me a second here. So I'll just paste it over here. So what are these two lines? We are just updating the heights after the rotation. Yeah, finally we have to return the new root. So for returning the new root, I'll just go with return x. Simple. Yeah, let me come out of this one entirely. I'll just go with def left rotate. Yeah, so I'll just pass x along with the self. X along with the self. First, similarly to the this one, y. So this will be y equals x dot right. We are going with a left rotation, right? Y equals x dot right. So this is fine. So let me assign the t2 to y dot left. Then y dot left, similar to the this one, rotate, right rotate. We are just going with the left rotate. Y dot left, let me assign this one to the x, and x dot right, let me assign this one to the t2. Yep, so this is fine. Finally, what we have to do, we have to update the heights of the rotation, right? So just give me a second here. So I'll just come here. Let me paste it over here. This is fine. So next what I'll do, let me return y. Let me return y. Yep. So this is fine. Yep. So next, let's write the function to insert a node and rebalance if needed. Right. So I'll just go with the insert method. Yep. So I'll just go with insert here. This is fine. Along with the self, I need root and key. Along with the self, I need root and key. So this is fine. First thing, let's go with a normal BST insertion, right? So let's go with a normal BST insertion. So let me paste this one over here. If not root, then we are returning this one. What do we call? 1 second. Yeah, if not root, then we are returning node of key. Key, if key is less than this one root dot key, then we are just assigning left to this one. We are recursing right here. We are going with the insert of root dot left comma key. Same thing goes with the right as well. Yep. Just the changes, instead of root dot left, we have given root dot right as we are going with the right subtree, right? So this is fine. Yep. The next step here, After the normal BST insertion, let's do one thing. Let's update the height of this ancestor node, right? So yeah, let me paste this one over here. Okay, so this is nothing but we are just updating the height of this ancestor node, right? Root dot height equals 1 plus max of get height of get height. We have already written that method, get height of root dot left, and uh, for getting the right subtree height, so we are going with the get height of root dot right. So we are just updating the height of this particular ancestor node. Next, we have to get the balance factor as well. Let me do one thing. I'll just go with balance here. Let me assign this one to get balance, get balance of root. Let me go with get balance of root, right? So this is fine. Next, we have to check the balance and we have to perform the rotations, right? So I'll just go with the left case, right? So if you remember, uh, we have to go with the left case as well as we have to go with the right case, right? And then we have to go with the left right case and the right left case. These four cases, right? So first, let's do one thing. Let's go with the left case actually. Why we have to go with these four cases? We have to check the balance and we have to perform the rotations actually based on the balance itself. We have to check the balance and then we have to perform the rotations. We have four cases. One is left case, right case, left case, and right left case. First, let's go with the left case. So I'll just paste it over here. This is left case, right? So if balance greater than one and key less than left dot key, then we just have to return the right rotate of this one root. Similar to this one, let's go with other three cases, nothing but right case next. So let me paste this one over here for the right case. So we are checking whether it is less than -1 and greater than root dot right dot key, right? So here we are going with the left rotate instead of the right rotate, right? So that's the difference between left case and right case. Next, let's go with a left right case. So just come here. Let me paste it over here. Now we are checking greater than one and key. So this one as well as the this one actually. Instead of the right, we will be going with the left. That's it. That's the only change actually here, right? So root dot left, we will be setting this one to the left rotate, which we have already written actually method. So we'll pass the root dot left, and we will be going with the self this one. Will return right rotate method here, self right rotate of. So this is fine. This is for the left right rotate. Similarly to this one, we'll be going with a right left rotation as well, or right left rotate as well. Not right left rotation, it's right left case. Sorry. Yeah. The last one here, right left case actually. Balance less than -1. This one as well as this one actually. Yeah. This one. Mixture of left right, right? So instead of the left, we are considering right. That's the only change again, right? So here root dot what happened here? 1 second. So this is fine, I believe now. Yeah, right. We are setting this one to the right rotate of. So in here we are going with left. We are setting the left to left rotate of left root dot left. Yeah, we are setting the right to right rotate of root dot right. And again, instead of the left, so this one we are going with a instead of the right rotate, we are going with the left rotate of. We are passing the root. Same thing. Yep. So this is fine, I believe. Next, what we will be doing, next what we have to do, we have to return unchanged node. Nothing but here we have to return the root, right? So I'll just return here root. Yep. So this is fine. Next, let me do one thing. Let's move on with the further things. There is only one function left, that is nothing but we have to write the function for in order traversal, which gives the sorted output, right? So I'll just go with def in order here. So I'll just go with self comma root, self comma root here. So this is fine. So let me go with simple if condition here. If not root, if not root, then let's just return. Yeah, let's just return. So else I'll just do one thing. Let me go with in order here. So this has to show in order, nothing but we are recursing here, right? So I'll just go with root dot left. What's the problem? Yeah, I have given comma here instead of the full stop. So this is fine. The next one is let me go with the print here. Print of let me pass the root dot key. So this is fine. Along with it, let me set the end to the empty string. Yep. So this is fine. The next one, in order, set dot in order, let me pass the root dot, right? This is fine. Yep. Next, let me do one thing. Let's go with the example usage. Example usage, usually I take it from the Google. Let me Google and or let me take the example from the Google. Just give me a second here. So let me come here. Let me paste this one over here. Actually, example. So what is the output that we need to get? We have to get the in order traversal of the constructed AVL tree in the sorted order, right? All the output that we need to get here is 10, 20, 30, 40, 10, 20, 25, 30, 40, as well as the 50, right? In the sorted order, actually. Yep. So yeah, accordingly with the example that we have considered. Yep. So we are just calling the AVL tree class here, the main class actually. This one AVL tree. Then what we are doing, root we are setting this root we have set this one to initially none. Nums we are passing numbers array, right? So next we are calling the individual nums and we are inserting the this one is static from the root we are inserting the numbers, right, then to the nodes, right? So then we are printing the in order traversal of the constructed AVL tree is, then in order we are starting the in order from the root actually, then we are printing the this one result. Basically we have to get the output 10, 20, 25, 30, 40, 50. Let's check the same. As we have the complete idea on the algorithm, we have discussed this one step by step, and so let's do one thing. Let's run the code. I'll just give control C here. Let me give control J. Yep, clear screen. I'll just go with Python followed by file name dot py, right? So I'll just give here. This is fine. Yep. Let me give clear screen. Yeah. Uh, 1 second. Showing line number 86. Insert AVL tree object has no attribute. Right rotate. Oh, well, let me change this one. 1 second. Where is it actually? Line number 86, right? 86. So let me change this one here. Right rotate. So let me change this one to 1 second. Yeah, I'll just change this one to capital R here. So let me clear screen again. Let me run this one. Yeah. So in order traversal of the constructed AVL tree is 10, 20, 25, 30, 40, 50, which we are getting in the sorted order. So we are getting the absolute correct output or the desired output, right? So see here, what is happening accordingly with the algorithm. So first we are considering this one. 1 second. Yeah, this example actually 10, 20, 30, 40, 50, 25. We have to get the output in the sorted order. So this is fine. First, first what happens here? So the numbers, whatever we have considered this numbers, 1 second, just give me a second. Yeah, this number, 10, 20, 30, 40, 50, and 25, these are inserted sequentially first. Yep. After each insertion, what happens? AVL tree, what it does, it checks the balance factor of every node. It checks the balance factor of every node, right? So whenever imbalance occurs, right? Whenever imbalance occurs, for example, after inserting 30 or 25, appropriate rotations are performed, right? Appropriate rotations are performed. So imbalance occurs meaning after inserting 30 or 25, imbalance happens, right? So 25 has to be before 30. According, we have to get the numbers in the sorted order, right? So after inserting 30 or 25, imbalance happens. So appropriate rotations are performed actually. Finally, the tree becomes balanced and in order traversal prints the elements in the sorted order. Nothing but we have got this one in the sorted order. 10, 20, 25, 30, 40, and 50, which is absolutely correct as per the code that we have written. Yep. So this is it for the this one. AVL tree algorithm. Very simple one. Yeah, very simple one. Let's do one thing. We are done with the algorithm. We have discussed the output part as well. Now, as we are done with the algorithm, before moving on with the next algorithm, let me summarize whatever we have learned so far. Right. So first thing here, there are some 2 to 3 points we have to remember. Just remember these 3 points. You have to remember these 3 points. Yeah. AVL tree is height. This one balanced binary search tree. AVL tree is nothing but height balanced. So I'll just write here height balanced binary search tree, right? AVL tree is nothing but height balanced binary search tree, ensuring big of log n complexity for all operations, ensuring big of logarithmic n complexity for all operations. So again, AVL tree is a height balanced binary search tree, ensuring big of login complexity for the all operations, right? So let's move on with the second point here. Second main point, it uses rotations. We know this one, right? So we have come to the ending part actually. It uses rotations to maintain the balance after insertion or deletions, right? So to maintain the balance actually, it uses rotations, right? I'll just write here to maintain balance, right? So this is fine. Yep. So the third main point here is, so this makes AVL trees ideal for the applications needing fast lookups and inserts, such as database indexing. So this is one of the this one use cases actually. It is used in the database indexing or memory management. So this is very important use cases where it is used actually. AVL trees. These are used in the database indexing and the memory management. Yep. So this is fine, I believe. So these are some of the points I wanted to discuss with you guys. This you have to remember this one at any cost, right? So this you have to remember these points at any cost. Now, as we are done with the AVL trees, next let's move on with the this one. What algorithm? Completely forgot. This one, Bloom filters algorithm. Yeah, let's move on with the Bloom filters algorithm next. For now, this is it. Thanks for watching, guys.